Okay. In case 2, we have repeated linear function. I'm sorry, repeated linear factors. Okay, in this case we have q of x has a factor of the form, it looks like a sub 1x plus b sub 1, except it raised to the power of r. What does it mean? It means that the factor, the linear factor a sub 1x plus b sub 1 is repeated r times. Okay, so the general structure is going to be the following. In this case, remember, after the long division and getting, when we get the proper rational function, let me actually do it, go right into the repeated linear factor. So if the denominator is a repeated linear factor, as I wrote here, a sub 1x plus b sub 1 raised to the power of r, how we gonna, what will be the partial fraction decomposition of this thing? Well, remember, we repeat r times, so the first one, the first fraction will be a sub 1 over the denominator. The next one will be a sub 2 divided by a sub 1x plus b sub 1 squared. And we keep adding powers until we get to the last one, which is the rth position, or the and we end up having a sub 1x plus b sub 1 raised to the power of r. For instance, if we have, actually, here's the example. For example, if we have something like this, let's say the numerator is a cubed minus x plus 1. The denominator is x squared times x minus 1 cubed. First of all, you can see that this is a proper rational function, because the degree of the numerator is 3, but the degree of the denominator is 5. So we don't need to do long division. Second, we have the factor, the linear factor x, or x minus 0, if you will, repeated twice, and the linear factor x minus 1 repeated 3 times. So we're going to break it down as a sub 1 over x plus a sub 2 over x squared. We are done with the first linear factor, and we'll do b sub 1 for x over x minus 1 plus b sub 2 over x minus 1 squared, and b sub 3, in this case r equal to 3, and we divide by x minus 1 cubed. Okay, so let's look at the next example, example 4, I believe. Okay, we need to evaluate the following. We have the integral, the numerator is a 4-order polynomial, x to the 4th minus 2x squared plus 4x plus 1. The denominator is x cubed minus x squared minus x plus 1 dx. Okay, so if you observe, you see that the degree of the numerator is greater than the degree of the denominator. So this is not a proper rational function. So we need to apply long division. Okay, so let's do the long division here. The denominator, the divisor, x cubed minus x squared minus x plus 1, that's a big one. And then the dividend is x to the fourth minus 2x. Okay, here I'll stop right there, because you see we are missing the x cubed term. And you need to think about it as a place value. Like x to the fourth would be the 10,000 digit, x squared is the 100 is the 1,000 digit. I'm sorry, the 100 digit. X is the 10th and 1 is the unit. So here I'll put 0 times x cubed to keep that place value, and then I have minus 2x squared plus 4x plus 1. Okay, so I have the 10,000, so to speak, the 1,000, the 100, the 10th, and the 1. And now to get to x to the fourth, I need to multiply by x. So I place it above the x value, the x place value. Okay, that's the advantage of using place values based on the power of x. So x times x cubed will be x to the fourth. X times negative x squared will be minus x cubed. X times negative x will be negative x squared, and x times 1 is x. And now we subtract. Again, this is another advantage of using the place value, is you subtract like terms. Otherwise, this will have x squared above the x cubed, and this is conducive to making mistakes. So x to the fourth minus x to the fourth is 0. We have positive x cubed, 0 plus x cubed, and then we have negative 2x squared plus x squared. That will give us negative x squared, and 4x minus x is 3x, and now we drop the 1, and we have x cubed, so we need to multiply it by 1, and 1 times x cubed, and we just drop everything here, and we subtract. So x cubed minus x cubed, x squared minus x squared, negative x squared plus x squared, 3x plus x is 4x, and 1 minus 1 is 0. So that's it, and we have nothing to drop here, so this is the remainder, 4x. Okay, so now we can say that our integral, I'll call it I because I'll go back to it, our integral, which originally was this thing, can be written now as the integral of x plus 1 plus 4x, the remainder, over the divisor, which is x cubed minus x squared minus x plus 1 dx. Now we have x plus 1, and then we have a proper rational function to continue. So we need now to find out the factors of the denominator. So a q of x cubed minus x squared minus x plus 1. To factor this, you can group it into two groups, x cubed minus x squared, and then negative x plus 1. Factor out the x squared from the first two and get x minus 1. Factor negative 1 from the second group, and what you get is x minus 1 as well. So what we see that we have x minus 1 times x squared minus 1. Okay? At this point, I can use the previous result because x squared minus 1 is the type of x squared minus a squared, and I know that I'll have the natural log of x minus 1 divided by x plus 1. I don't want to do it because I want to show you how to deal with repeated linear factors. But in the future, you can, if you recognize something like this, you can say, aha, I can use the previous result. So x squared minus 1 is really x minus 1 times x plus 1. So here's your repeated linear factor, x minus 1 squared times x plus 1. And this is what we'll take to the next page. Okay. I'll pause for a second here to let you catch up. We are ready to write the partial fraction decomposition. This is the remainder only, 4x over x minus 1 squared times x plus 1. And the decomposition will be the following. We have the x minus 1 repeated twice. So we have a1 over x minus 1 plus a2 over x minus 1 squared plus b1 over x plus 1. As before, we're going to multiply by the LCD. And we lose the denominator. On the left side, we'll have 4x. On the right side, remember, this is the common denominator right there. So a1, we need to multiply it by what? By x minus 1 and by x plus 1. a2 need to be multiplied. Well, it's multiplied already by, it has x minus 1 squared. So all we need is x plus 1. And a and b1 will be multiplied by x minus 1 squared. You can see that the technique that we had, the shortcut won't work here, because if we let, for instance, x equal 1, we can get a equals a2. That's fine, but if we let x equals negative 1, actually it may work. No, because of the square. I'll compare coefficients. So to do so, I need to clear the parentheses and write in terms of what multiply x squared, what multiply x, and what multiply 1. Okay. So let's see, what multiply x squared? Well, I have x squared, so I have a1, and here I don't have x squared, but here I have x squared minus 2x plus 1, so I have a1 plus b1. What multiply x? Well, here I have x squared minus 1, so I won't have anything here. I have a2, and here I have negative 2x, so I have minus 2b1. And what are the free coefficients? I need more room here, because I have a free coefficient will be a1, no, negative a1 from the first one. Let's make room. And I have plus a2 from here. And here I have, at the end, I have plus 1, so I have plus b1. Okay, so those are the free coefficients. And now we compare coefficient. And let's see. We have on the left we need to write x squared x in a 1. And let's see, the coefficient of x squared on the left is 0. The coefficient of x squared on the right is a1 plus b1. So we get a1 equal negative b1. The coefficient of x on the left is 4. On the right we have a2 minus 2b1. And the coefficient of 1, we have no free coefficient, so it's 0. So negative a1 plus a2 plus b1 equals 0. Solve this, put it in a matrix form, or solve it by substitution or any other technique, row echelon reduction, and the solution is a1 equals 1, a2 equals 2, and b1 equals negative 1. So this is, we get the partial fraction decomposition. Now we need to go back to our integral I. So I equals what? Go back here, we have x plus 1. This is the whole part after the long division. And what we did is we did partial fraction of the remainder. Remember? So we still have the integral of x plus 1. And then we have these, the three components that were the partial fraction decomposition of the remainder. So it will be 1 over x minus 1 plus a2 is 2 over x minus 1 squared minus 1 over x plus 1. So now we are ready to integrate. This is the easiest part. So we have x squared over 2 plus x. This will be the natural log of the absolute value of x minus 1. Okay, what will be the interval of the fourth terms here? Can you tell me? Ooh, this is suspicious quiet. Make x minus 1 equal u. So you have the integral of 2 over u squared dx, okay? So it's u to the negative 2. The integral or the antiderivative will be negative u to the negative 1, or negative 1 over u, or negative 1 over x minus 1, right? But we have the 2, so we have minus 2 over x minus 1. And here, this is simply the natural log of the absolute value of x plus 1 plus c. Now look at these two terms. You can simplify and end up having x squared over 2 plus x minus 2 over x minus 1 plus the natural log of the absolute value of x minus 1 over x plus 1 plus c. When you review this particular exercise at home and you take it a step back, you can see that we actually could have solved it quicker and without needing the repeated linear factor, because you should recognize this result as something that we've done before. Okay, is coming from here when you have x squared minus a squared. Okay, and where do you see it? If you stop at this point right here, you have the x plus 1 plus two factors. One is x x minus 1, and the other is x squared minus 1. Okay, so you do a smaller partial fraction decomposition. You have the something over x minus 1. Well, that will be this component, and then you have something else over x squared minus 1, which will lead you to this result. So it's a little bit quicker if you solve it this way.